Hello, welcome to all. In the previous lecture, we studied the background to this Maxwell's equations. We studied the modifications of Ampere's law, okay, and displacement current. Okay, actually, this concept is very important, and it paves the way for the Maxwell's equations. Okay, in the today's lecture, we will study about the Maxwell's equations in integral form, Maxwell's equations in differential form, okay, and Maxwell's equations in free space, and Maxwell's equations in a material medium. Okay, right. Actually, the discovery of the displacement current is a starting point for the Maxwell's equations. What is the importance of Maxwell's equations? Okay. Maxwell's equations are the set of fundamental equations giving the unified theory of electric and magnetic fields. Okay. So far, we considered electricity and magnetism as two different branches. Okay. Later on, we studied the electromagnetic induction. So after that, by writing down the Maxwell's equations, we are able to uh, study the electricity and magnetism in a unified view. From the single theory, you can study all the content of electricity and magnetism. Okay, that is what the importance of Maxwell's equations or the Maxwell's theory of electromagnetism, okay, or Maxwell's electromagnetic theory. Now, first of all, let us go for the integral form of Maxwell's equations. Okay, these Maxwell's equations are nothing but the summarizing the entire basic laws from electrostatics to magnetostatics and electromagnetic induction with just one change in the Ampere's law. Okay, by default, we get the Maxwell's equations when we summarize all these fundamental equations. Okay, when you write together all these fundamental equations, then we will be getting the Maxwell's equations in integral form. Okay, yeah. So what's our topic? Maxwell's equations. Maxwell's equations. Now we are going to study the Maxwell's equations in integral form. Okay. First, let us study the Maxwell's equations in integral form. Maxwell's equations in integral form. Okay, let us write down one by one all these four equations. Yeah, first let us start from the electrostatics where we have the Gauss law. Okay, integral E dot ds is equal to q by epsilon naught. Actually, we are writing this as a Maxwell equation, but actually, what is this? This is the Gauss law of. Okay, you can see this on the slide as well. Gauss law of electrostatics. Gauss law of electrostatics. Okay, now I will go for the second equation. Okay, to write this second equation, we are going for the magnetostatics, where we have the similar equation. You may call that the Gauss Law of Magnetostatics. Okay. Integral B dot ds is equal to 0. Integral B dot ds is equal to 0. We may call this as, we are writing this as a second Maxwell's equation. Okay, we are writing the set of equations. Yeah, this is nothing but Gauss law of magnetostatics. Gauss law of magnetostatics. Okay, after this we are going for the after this we are going for the next Maxwell equation. For that we are going for electromagnetic induction. Okay. So next I am writing the Faraday's law as a next Maxwell equation. What is that? Integral. What is that? Integral E dot dl. Integral E dot dl. Integral E dot dl is equal to minus of integral. You have dou psi by dou t, na? Psi is integral b ds. So you have minus of integral dou b by dou t dot ds. Yeah. What is this? This is actually Faraday's law. Faraday's law. Okay. Next, let us write the last Maxwell's equation, which is nothing but the uh, Ampere's law with Maxwell correction, or the modified Ampere's law. What is this? Integral B dot dl. Integral B dot dl is equal to mu naught I actually. So I'm writing it into the integral with modified term. So j mu naught integral j plus corrected term, Maxwell's correction, epsilon naught dou E by dou T, okay, into ds dot ds. This is what, this is the modified Ampere's law. What is this? This is the modified Ampere's law, right? Yeah, now these are the Maxwell's equations in integral form. Okay, you are seeing all the integrals. You can see the same equations on the slide as well. Okay, these are the this set of equations are called as the Maxwell's equations in integral form. Why? Because you are having all the integrals here. You are having all the integrals here, right? Now, what is the importance of this set of equations? If you are taking only this set of four fundamental equations, you are able to get the entire content of electrodynamics. When these equations are supplemented with the Laurent force equations, what are the other equations to necessarily describe the entire electromagnetic phenomena? Laurent force equation. What is that equation? F is equal to F is equal to Q E plus V cross B. E plus V cross B. This we call this as the Lorentz force equation. It gives you the force acting on a charge placed in the electromagnetic field. That means where you have both electric and magnetic fields. Then you have electrostatic force as well as magnetic force acting on the charged particle. Okay? Yeah. Whenever you supplement Maxwell's equations with this Lorentz force equation, then you are able to describe completely the electromagnetic phenomena. Okay, so that's why this set of four equations assume some under fundamental importance. Okay, this is actually Maxwell's theory is the first unified theory of any kind. Before that, we didn't had any unified field theory. Why it's a unified field theory? It looks electric and magnetic fields in some unified view. Unified view. That means you see, whenever you see the content of these four equations, you can easily understand this. And because here electric and magnetic fields are not separate. Okay, both electric and magnetic fields are interlinked. That you will see in this Maxwell's equations. Okay, here the important thing is variations in magnetic fields are creating electric fields are the it is inducing EMF. Okay, similarly here the variations in electric fields are creating the magnetic fields. This is due to the Maxwell's correlation to the Ampere's law. So we can understand from this electric and magnetic fields in a single point of view. Single point of view. Okay. Yeah. If you take the first Maxwell's equation, you know this is the Gauss law of electrostatics. Okay. You know here on the right side you have the source of the field on the left side. Okay. This is source of the electric field. If you go for the Gauss law of magnetostatics, by seeing that equation, you can say that there are no magnetic monopoles in the universe. That means there are no isolated magnetic charges. Okay. So on the right side of these two equations, you have electric and magnetic sources. Okay, or charges. What is a magnetic charge? Zero. You don't have magnetic monopoles in the universe. Okay. Next, whenever you go for the third Maxwell's equation, it is nothing but simply the Faraday's law. Yeah. Here, the variations of magnetic fields are creating the electric field. On the left side of this equation, you have E, electric field, E, okay, or the entire thing you know that EDL is nothing but EMF. It is related to the electric field. Similarly, if you go for the last Maxwell's equation, that is a modified Ampere's law, here also On the right hand side, you have variations in the electric field. Okay, these variations in in electric fields are creating magnetic field. Okay, that can be seen by having a LHS as integral BDL. So here there are some similar origins of electric and magnetic fields. This is visible in Maxwell's third and fourth equations. Okay. Yeah, actually, we are just writing them by one, but you did not designate one with first Maxwell equation, second Maxwell equation. Okay, you need not to do that. This set of fundamental equations is known as a Maxwell's equations. Maxwell's equations. What they are conveying to us, these equations are giving all the essentials or the gist of electric and magnetic fields. Electric and magnetic fields. Okay. That is what the importance of this Maxwell's equations. Okay. Maxwell introduced these equations in the year 1862. Okay, this was the first unified field theory. Field theory. You know that today there are more modern versions of field theories, unified field theories like the theory of everything. Okay, what is the inspiration for all those theories? This Maxwell's theory. Okay, after that, Einstein tried to unify the gravitation with this uh, magnetic fields. So, what is the starting point for all these unified field theories? This Maxwell's theory of electromagnetism. That is what the importance of Maxwell's equations, okay, which constitutes the Maxwell's electromagnetic field theory. Okay, right. After studying the Maxwell's equations in integral form, we are going for the Maxwell equations in the differential form. Maxwell equations in the differential form. Yeah. When you write the Maxwell's equations in differential form, we see them in a compact form. Okay? In a very simple and beautiful form. So we convert the Maxwell's equations in integral form into differential form. Okay, which we are already done in the previous lectures. We are already done in the previous lectures, but you can see now uh, all those differential forms together, known as the Maxwell's equations in the differential form. Okay, whatever we are studying, whatever the Maxwell's equation we are studying now, just now we wrote in integral form, and now we are writing in the differential form. All these Maxwell's equations refer to the free field or vacuum. Okay, these Maxwell's equations does not refer to any medium. Does not refer to any medium. Okay, later on we will go for that. What first Max? Let us write the first Maxwell's equation. Yeah, because we are already converted all these equations in different lectures. I am just writing down these equations. Okay, I am just directly transforming this Maxwell equations in integral form into differential form. So, what is Gauss law in differential form? Del dot E is equal to rho by epsilon. You can see my lecture on electrostatics, okay, in order to convert the Gauss law of electrostatics into differential form. Okay, we already derived this expression. Next, second thing is the Gauss law of magnetostatics. You may write the similar equation del dot B. Why? Because the first two equations are similar, integral forms are similar, differential forms are also similar. On this side you have 0 there, so you have 0 here. Del dot B is equal to 0. Next, let us go for the Faraday's law. Yeah, we studied the Faraday's law in differential form, actually, in electromagnetic induction unit. Okay, uh, let us just write down that Faraday's law in differential form. Yeah, this is del cross E is equal to minus of dou B by dou T. Minus of dou B by dou T. Right? Next, let us go for the modified Ampere's law, because Faraday's law and modified Ampere's law are very much similar. Then we have similar differential equations, except with the change of E and B. That is what the beauty of Maxwell's equations. Here you have the sources for the what is this? Sources for the electric field or the current. That's why you have one more additional term, mu naught J. See, whenever you are writing this in a differential form, here you are writing J instead of I in the actual Ampere's law. Yeah. Even in integral form, we wrote the with I in terms of J plus mu naught epsilon naught. Okay, you can see this on the slides as well. Dou E by dou T. Dou E by dou T. See, you see this set of equations known as Maxwell's equations in the differential form. See, there is no integral symbol in all these equations. That's why we call these equations as Maxwell's equations in the differential form. See, you are having two dot products and two cross products, or two cross products, two dot products. All the products are with the del, okay, del operator. Okay, once del is operating on E as a dot product, one we are operating del on B as a dot product. Once we are operating E with cross product with E, once we are operating del with a cross product on B. Okay, so we have two dot products and two cross products, one on E and one on B. This gives you the four Maxwell's equations in a differential form. Yeah, to understanding the physical content of these four equations is very important. Just now we discussed in case of integral form. So the physical content remains same whether the equations are in differential form, whether the equations are in integral form. Okay, they convey the same thing, but some form may convey some in some easy manner the physical content involved here. Some forms may does not simply give you the physical content just by looking those equations. And that is what the difference. But the essence of two forms of the equations is same. Both are equivalent. Both are equivalent. But the in differential form, you find the Maxwell's equations in very compact form. Okay, in very compact form. Right? See, on the first two equations we have on the RHS's right hand side of those two equations the sources of electric and magnetic fields. Here you have currents. On this side you have currents. This is the electric current. Here you don't have any. Okay, on this side you don't have any charges, that's why you don't have any currents for magnetic field. Here you have the variations in B. Here you have the variations in E. Variations in B are producing the electric field. Variations in E are producing the magnetic fields. This is what the beauty of Maxwell's equations. Okay. Yeah, here we are seeing both E and B on equivalent basis. Okay. See, variations in E is able to produce the magnetic field. Similarly, what Maxwell assumed, variations in E also produce the corresponding magnetic field. This is what the um, assumption of Maxwell. Okay, this is not the only assumption. Later on, this was confirmed experimentally. Okay, in the Hedge experiment. So what the Maxwell correction is doing here, actually deriving the Maxwell's equation is nothing but modifying the Ampere's law with Maxwell's correction. That we have to know. That itself forms the theory of electromagnetism or electromagnetic waves or the Maxwell's theory of electromagnetism. Okay, right. That is very important. Yeah, that is making the electric and magnetic fields very much similar. That is keeping them on equal footing. Okay. Here we are looking some symmetry in two fields. Okay. That is only possible with the Maxwell correction term in the Ampere's law. Okay. See, nothing is instructed Maxwell to introduce or to make the correction in the Ampere's law. Just by looking for the symmetry from the theoretical considerations, Maxwell tried to rewrite the Ampere's law. That we have to know. Okay? But finally, that was confirmed by the experiment, and that gave us the theory of electromagnetic waves. Very successful theory. But it started from the uh, for some intrigue for the completeness in the theory of electromagnetism by the way of proposing the displacement current. Okay, this we have to know. What guided the Maxwell to make the correction in the Ampere's law? The only theoretical, from the theoretical point of view, he saw some flaw in the Ampere's law only on the theoretical grounds. Okay. Otherwise, what we call some aesthetic sense. Okay. In order to make it more complete and more beautiful, he introduced one more term called displacement current in the Ampere's law. That is what actually paved the way for the theory of electromagnetic waves. That we have to note. You see, all the four equations are very, very fundamental in nature and very, very similar to each other. You take the first two equations, you may define you may define del for E, you may also define del for die for B. You may define die for E, you may define divergence for B. Okay. Uh, Similarly, you may define curl on E and you may define curl on B. Okay, on the RHS side, the first three equations is very much similar. The RHS of the last two equations, the RHSs of last two equations are also very much similar. You may ask me why there are two terms in the last equation, why there is only one term. Because there are no magnetic charges, that's why you have no magnetic currents here. So you have no first term. Okay, there is only one term you are having in the third Maxwell's equation, that is Faraday's law. Okay, but here the Maxwell seeing all these equations from some symmetric point of view. Okay, is looking this set of all the four equations in some aesthetic sense. That is what paved the way for the unified theory of electromagnetism. Here we have already studied all these equations in respective units, topics, but here we are looking all of them with a single point of view. Single point of view. We are comparing each one with the other thing. Then we have the set of equations known as Maxwell's equations, giving us the theory of unified field theory of electricity and magnetism, or electric fields and magnetic fields. Okay. Yeah, this is what the importance of Maxwell's equations. Actually, the Maxwell's equations predicted the unknown waves known as electromagnetic waves. Later on, it was confirmed that those waves are nothing but the light waves, because though those waves travel with the velocity of light. Right? This was experimentally confirmed by the heads. Right? So we may predict something physical from the unphysical origins. That means just by the mind work, we can imagine something that is there in the physical universe. Okay, the same thing happens in the case of Dirac's discovery of positron. Okay, so these things are creating some miracles in the physics. Okay, such beginnings. Okay. Yeah. Now, whatever the equations we discussed so far, all those equations are not referring to the properties of medium. Okay. Yeah. Now let us go for the Maxwell's equations in dielectric medium. Okay. So far we discussed the Maxwell's equations in free space. Okay. Now we are discussing Maxwell's equations in a medium, or the dielectric medium. Let's go for the Maxwell's equations in dielectric form. Dielectric medium. Now the Maxwell's equations reflect the properties of medium. Okay, whenever you write those equations for one particular material medium, we are taking dielectric materials. Okay. Yeah, I think you know about the dielectric materials. Yeah, in those materials, there is no chance to the charges flow from one part of the body to other part of the body in dielectric materials. Okay. So whenever you place dielectric materials in electric field, okay, the charge distributed all around those materials will drift towards either one end of the one surface of the dielectric or the other surface of the dielectric. We call that process as a polarization. Polarization. So in dielectric medium, you have polarized charge. You have some induced charge known as a polarization charge. Polarization takes place. Okay, so you have some additional phenomena in the dielectric media. So, dealing with the dielectric media is a little bit complicated. So, whenever you try to write the Maxwell's equations for a dielectric medium, it becomes a little bit complicated. Okay, we will see now. You may also expose the magnetic material to some external dielectric material to some external magnetic field. Okay, that may induce some current inside the dielectric material. So now we are going to take into consideration all these things. We are considering all these induced charges, all these induced currents. Okay, now we are including them in the Maxwell's equations. So you have electric polarization as well as magnetic polarization. Whenever you place the dielectric material in an external electric and magnetic fields respectively. Why? Because if you take any molecule of that material, actually those molecules are tiny magnets. So those molecules are affected by the magnetic external magnetic field. So you have you have some current, some current due to the flow of that charge in the external magnetic field. In external magnetic field. Okay. You also have one current due to polarization. We call that as a polarization current. Polarization current. That is due to the motion of that uh, polarized charges. Okay, we have to include all these currents and charges in the respective Maxwell's equations, because in Maxwell's equations on the right hand side you have all the charges, both the electric and magnetic, and the current, electric and magnetic currents. Yeah, just now I told you that there are different charges and there are different new currents in the dielectric material. Okay. See, what will be the bound charge? What will be the density of this induced charge? Polarization charge, density of the polarization charge. We call this as the bound charge density. So how many densities in differential form? You have charge density and current density. That's why we are writing for these induced charge densities. Okay, one is bound charge density. You have polarized charge density or bound charge. Why? Because these are all the things bounded to that dielectric material. Okay, you will see all these things within the surface of that dielectric material. Bound charge density. Bound charge density. Okay, so now you have some additional charges, additional current in the dielectric materials. One such charge is bound charge or polarization charge. You are writing the density of that charge as a, okay, you can see that on the slide as well. Rho B bound charge. This is given by del dot P. What is P? Polarization vector. This charge density is given by this dot product, right? Next, you have current density due to the magnetic field. Okay, we have this charge density due to external electric field. Now we call this magnetic current as a bound current density. Bound current density, that is yeah, you call this, we denote the current densities with J, na? So you have J, B, okay. This is expressed as a curl with magnetization. Yeah, this is a magnetization vector, this is a polarization vector. No? Okay, we call M as a magnetization vector. See, whenever you place the dielectric material, some magnetization is taking place, alignment of those tiny magnets within the material. So you have magnetization that will give you the bound current density. Okay. Next, here you have one more current or current density due to the change in the polarization, due to the change in the polarization, okay, due to the drifting of positive charge and negative charge to the surfaces, you have one more current known as a polarization current. Polarization, this is of electrical origin. Polarization current, yeah, you may call this as JP, okay. Otherwise, I will write here. Next thing, polarization current. Third thing, polarization current JP, as I already told to you, this is due to the variation in the time variation in the polarization of dielectric material. Okay, right. Now we have all these additional currents and the charges, current densities and charge densities. Okay, in the total current density or the charge density. Okay, now you have to split your charge density and current density into different parts. Why? Because all these parts are making the total current density or charge density. Okay, now we will see what will be the total current density and what will be the total charge density. Okay, yeah. Now I will write here, otherwise somewhere here. Yeah. See here, actually, earlier, before coming to this dielectric materials, we have already having free charges and free currents. That's why we do not those densities the foot, yeah, free charge, okay, something like that, free current. Yeah. So otherwise, I will write here. Yeah, you see here. Here I am writing the total charge density to be, yeah, free charge density. This is default one. Now we are having additional charge density. What is that? Rho B. So now you have here, you need not to express, write anything for this, but for this thing you have minus of del dot P. So in the place of rho in the Maxwell's equations, you have to write rho F minus del dot P. Okay? Already you are having this thing there. You are adding one more term due to polarization. Okay. Next, let us go for the current densities, J's. What is the total current density, J? Okay. This is equal to you combine all the j's. One is default one, this is j. Let us call f, okay, free current density plus other two current densities due to magnetization and polarization. Okay, you write j polarization, j magnetization. Okay, now you write the expressions for jp and yeah. Now you write the expressions for jp and jv. So now you have j is equal to what is jf? Okay, it is default thing. So far we wrote this as j only. Now we are writing this as jf plus what is jp minus dou p by uh, what is this? jp is equal to dou p by dou t. Dou p by dou t. Right? Here jp is dou p by dou t. jp, what is jp? Let us write this before writing that one. Del cross m. Okay. jp is over. Now jp we introduce finally jp. No? That's why this is dou p by dou t. Dou p by dou t. Okay. Now here we have to express the Maxwell's equations one by one with this current and charge densities. Okay. Now let us go for the first one. You need not to change the second and the third Maxwell's equation for free space. Why? Because those equations are not involving any currents or charges. So you have to modify only first and last Maxwell's equations in order to get the Maxwell's equations for the dielectric medium. Okay. So let us consider the first one, Gauss law. Gauss law of electrostatics is, what's that? In differential form, particularly we are interested in del dot E is equal to rho by epsilon. Rho by epsilon naught. Now what is your rho? We take from here. This is equal to rho f minus del dot P by epsilon naught. By epsilon naught. Okay. Yeah. Now let us write these del terms together. Yeah, for that you first write, you multiply this epsilon naught here. You just write epsilon naught E. On this side you have rho f minus del dot P naught. Okay. Now this is dot. So you may write this P plus epsilon naught E or epsilon naught E plus P on this side with dot product. On this side you are only left with rho f. Rho f. Okay. Since here this is known in dielectrics as D. Okay, displacement vector. Since D is identically equal to this epsilon naught E plus P, we have del dot D is equal to rho f. Yeah, this is what the first Maxwell's equation for the dielectric medium. Dielectric medium. Okay, right. Next, similarly, let us try to modify the modified Ampere's law, okay, for dielectric materials. Okay. Now let us go for the, okay, let us write down this equation here. Del dot D is equal to rho F. You can, okay. Yeah, before going to the Ampere's law, let us write down this equation here. Okay, del dot D is equal to rho F. Okay, just keep it aside. Next, we will go for the Ampere's, modified Ampere's law. According to modified Ampere's law, we have del cross B is equal to mu naught J plus mu naught epsilon naught dou E by dou T. Here we are now bothering about the currents because your total current is now a part of some currents, okay? Some of the different currents. So now you write for J, then you have epsilon naught, you take this expression here, JF plus del, or I simply write del cross M plus dou P by dou T. Dou P by dou T. Okay? Yeah, this is about this J. Now we are still having one more term, mu naught epsilon naught dou E by dou T. Okay? Now, let us try to do some manipulations in order to get the final equation. Okay, you see, you group together these terms with del. Yeah, this term and this term. Here, you write del cross. Here you are having B. When you bring this term to the LHS, then you get minus of mu naught M. Mu naught M. Okay, is equal to, on this side you are left with other terms, mu naught JF plus mu naught dou P by dou T plus mu naught epsilon naught dou E by dou T. Okay, right. Now, if you divide on both sides with mu naught, what happens? Or here you may get this B by mu naught minus M. This is equal to this mu naught, okay, is common. Okay, that's why we are writing this on the LHS as denominator. Then you have B by mu naught minus M. Mu naught cancel here. You are left with the terms without mu naught. Okay, JF plus dou P by dou T plus epsilon naught dou E by dou T. Okay. Now, what is this? This is nothing but H. We call this simply magnetic field. Magnetic field, or yeah, B is a magnetic induction vector. This is just magnetic field vector, or the magnetic intensity vector, right? Since, okay, I will write here otherwise. Okay, since H is identically equal to B by mu naught minus M, you have del cross H is equal to this thing, the entire thing. Okay, JF. Yeah, but here on this side also, you write JF plus, here you may take dou P dou by dou T common, so then you have P plus epsilon naught E again here. Okay, just now we defined this P plus epsilon naught E. What is this? This is nothing but electric displacement vector. Okay, so this is equal to, now you have JF plus, what is this? This is d. Dou d by dou t. On this side, what you are having? Del cross H. Okay. Yeah, this is the last Maxwell equation in case of dielectric medium. This is the first Maxwell's equation in case of dielectric medium. Okay. Now we have the Maxwell's equations for the dielectric medium. Okay, let us write them together. Yeah. See what's up. So now you have the Maxwell's equations for the dielectric medium as del dot D is equal to 0, del dot B is equal to 0, del cross E is equal to minus dou B by dou T, del cross H is equal to dou D by dou T. Dou D by dou T. Yeah, these equations are very simple. Okay, even very simple compared to the case of free space. Why? Because we are not having either mu naught or mu's or okay epsilon naught. Actually, all those things are absorbed in our auxiliary quantities. Okay, this d and all those things or this h. Right? That's why these equations are looking very simple, very simple. Okay. Okay. Let us stop with this. Thank you.